Welcome back, everybody. In this video, we'll be taking a look at two capacitors. This problem will force us to think about when we connect various capacitors, what quantities are and are not changing. So let's take a look at the problem statement. A capacitor of unknown capacitance C, it's charged to 100 volts and connected across an initially uncharged 60 microfarad capacitor. If the final potential difference across a 60 microfarad capacitor is 40 volts, what is C? I've drawn the initial situation up here. And before we start, why don't we go ahead and remind ourselves the definition of capacitance. It is charge per voltage. In other words, for as many volts as I can put on the capacitor, how much charge can I hold? We're given the problem that the capacitor is initially charged, and it has an initial charge of, or initial voltage of 100 volts across the plates, and we're looking for the capacitance across this guy. Now let me draw the final situation. In the final situation, we've connected this to a second capacitor. So I'll draw them both here, connected. And we're also given that the second capacitor has a voltage of 40 volts, and we're given its capacitance is 60 microfarads. Now what we need to decide in this problem, like any problem in which you're changing things in capacitors, it could be hooking it up to a battery, it could be grounding it and uncharging it, it could be changing its geometry. In those kinds of situations, the first thing we need to be entirely clear on is what quantities are and are not changing. So on your own, I'd like you to find out of the quantities describing the first capacitor, what is and is not changing. So find out of the quantities Q, delta V, and C, and I'll go ahead and label this Q and minus Q up here. Out of those quantities, what's changing? Take a minute now and pause the video if you need to. Let's first consider the charge. When the plates are connected, there's a excess positive charge on the top plate and no net charge on the bottom plate, which means there's a potential difference between these two plates. Since it's conducting, charges will move freely to cancel out that potential difference. So we know that the excess of positive charge on the top plate will actually be reduced and some of it will move to the bottom plate. So that tells us that the charge initially on the top plate decreases. Now let's look at the capacitance. The capacitance only depends on the geometry and the material properties of the capacitor itself. Since we're not changing the spacing, the size, the width, or what the capacitor is made of, the capacitance should not change. So C is the same. And then finally, using this equation, we know that since charge is decreasing, capacitance is the same, the voltage must also decrease. So we have that the voltage on the first capacitor has decreased after it's connected to the second one. So to reflect these changes, I'm going to just call these by some different variables. So we'll say that the voltage on the first capacitor after it's connected is called V1. The capacitance is still the same, so we'll just call that C1. I'll just call that C. And then the charges have changed as well, so we'll call the initial charge Qi. And the final charge, we'll call it Q1 on the top plate and minus Q1. And I'll draw a few less here to indicate that it's decreased. And on the bottom plate, we'll call it positive Q2 and minus Q2. Now there is actually a relationship between the charges on the first plate, in the initial situation and the final situation. And I'd like you to kind of figure that out on your own. So let me write that here as relation. There's a couple relations, but we'll start with the charge one. The first one is, well, let's go ahead and do this one, and I'll have you guys figure out the second one on your own. The first one, we know that the charge in the first plate has redistributed amongst the two plates here. And because air is an insulator, it can leave the situation. So the initial charge in the first plate must equal the sum of the charges in the last two plates because it can't go anywhere. So that tells us that the initial charge equals the sum of the charges in the last two plates. Now this on your own, figure out the relationship between the voltages. There's a relationship between these three voltages here, some of them or all of them. Try to figure that on your own, and pause the video now if you need to. We'll come back in a moment and take a look. What we have here is two conductors that are both in equilibrium. So the voltage at any given point in the conductor on this conductor on the left and this conductor on the right has to be the same. In particular, if the voltage down here, we know the voltage difference is 40 volts, so if this is 40 and this is 0, anywhere along this conductor, including the plates and the wire, has to be 40 volts. If there were voltage differences, the charges would redistribute and would not be in equilibrium. So given the fact that the bottom capacitor holds a voltage difference of 40 volts, the top capacitor must also hold a difference of 40 volts. So let me go ahead and write that down as delta V1 equals delta V2, because these guys are in equilibrium. And that tells us immediately that since the bottom potential difference is 40 volts, the top one must also be 40 volts. And now we can solve for a lot of missing quantities just using the capacitor equation many times. So let's go ahead and do that. And the first thing we can solve for immediately is the charge on the bottom capacitor, because we know its potential difference and its capacitance. Rearranging that equation, we have that the charge in the bottom capacitor equals the capacitance times the voltage difference, which is 60 microfarads times 40 volts, which gives us 2400 microcoulombs, sorry. All right, so that one was easy. Now we can also actually solve for the capacitor, the first capacitor. And to do that, you need to do a little bit of algebra, and you also need to use the charge conservation equation. So go ahead and try that on your own. Take a minute now and pause the video if you need to. Applying the capacitor equation to the first capacitor after it's hooked up, we get the following equation. We get Q1 equals C times delta V, so it's 40 times delta V, 40 volts times C, sorry. And then applying the capacitor equation to the initial capacitor, the first capacitor before it was hooked up, we get Qi equals 100 volts times delta C, times C. And then plugging these three quantities into the charge conservation equation, we find the following equation, which is that Qi equals Q1 plus Q2, so you have 100C equals 40C plus 2400 microfarads. And then just carrying out the simple algebra, that'll give you that the capacitor, the first capacitor has a capacitance of 40 microfarads. So this problem is not particularly hard, but it is very subtle. And as I've mentioned a few times, the first thing you have to do is consider what quantities are and are not changing. And it's not always going to be the case that, for example, the capacitance doesn't change. A situation like that would be if you had this capacitor and you hooked it up to a battery and then started changing how wide the plates are. In that case, because it's hooked up to a source of constant potential, delta V would be the same, but the capacitance would change, and then Q would change accordingly. So in these types of problems, the first thing you always have to do is ask yourself what quantities are and are not changing, and then proceed from there. Let's take a look at the summary of the problem. In this problem, we were asked to find the capacitance of a capacitor using its state after it was hooked up to a second capacitor. The first thing we did was we identified the quantities that changed after connecting the second capacitor, and then we identified some relationships between the charges using charge conservation and between the voltages using notions of equilibrium. Finally, we solved the equation piece by piece using the capacitor equation and the values given. So that's all for this problem. Please feel free to leave comments and questions on the link accompanying the video, and we'll see you guys next time.